Welcome everyone. I'm Tracy Fitzpatrick and I'll be your moderator today. Thank you so much for joining us here at Netcom Learning, a market leader in promoting lifelong learning, training, and talent development solutions. Hello everyone and welcome to today's session, BigQuery 2026 on Google Cloud, Performance, Cost, and AI Readiness. Presenting today's topic is Francisco, a seasoned machine learning engineer with over 10 years of experience in cloud and AI solutions. He specializes in designing scalable, secure data and AI architectures across AWS, Google Cloud, and Azure, helping organizations turn data into real business impact. With strong expertise in data engineering, analytics, and production-ready AI system, he brings a practical multi-cloud perspective to enterprise AI innovation. Bear in mind that this is an overview of a very robust topic. We offer a collection of technical and business courses that can be tailored to your specific requirements. If you are interested in a further discussion, you can make an appointment with our learning consultants through our website at netcomlearning.com. Today's session is also being recorded, so you'll get free access to the recording in the next 24 hours via email. Netcom Learning helps customers build innovative learning organizations by achieving a smarter workforce, adapting to change, and driving growth. We do this with a broad catalog of offerings, developing customized learning plans, and our global delivery capabilities. Since 1998, we have been empowering organizations with our managed learning services to help them reach optimal performance results and address challenges. We do have 9 practice areas in which we specialize. They encompass people, process, and technology training. Today's presentation is from the Cloud Practice Area. Netcom Learning offers a comprehensive training portfolio of courses for the topic being covered today. Our upcoming classes include various trainings on the given courses. You can also access a variety of marketing assets, such as the free training and blogs, by clicking on the available event handout. These offerings can be found with a simple search on our website at netcomlearning.com. In this webinar, data engineers, architects, and analytics leaders will learn how to optimize workloads using Google BigQuery on Google Cloud for improved performance, cost efficiency, and AI readiness. We'll cover best practices such as schema design, partitioning, clustering, materialized views, and slot management to accelerate queries while controlling costs. The session will also highlight governance and security capabilities, including row and column level security, encryption, and audit logging. And finally, you'll explore how BigQuery supports modern AI use cases such as vector search, embeddings, and RAG, helping organizations build faster, more scalable, and AI-ready analytics platforms. Now I would like to give you a quick overview of the logistics before we get started. To begin with, you do have the option to view in full screen by clicking on the full screen button on the right side of the GoToWebinar viewer. Simply hit the escape key to exit the full screen. Everyone has been muted except for our presenters. Feel free to submit any questions you have for the presenters here in the questions pane, and we will address them at the end of the session. And to get the best out of today's events, we've included the slides, courses we talk about, and marketing assets in the handout section of your GoToWebinar viewer. You may refer to them at any time to get a better understanding of today's topic. And we do realize that some of you may have to leave early and want to let you know that as you do leave the session today, you will be presented with a short survey. We would like to request for you to take a quick moment to participate in that survey. Your feedback really helps us understand your learning experience and improve our future sessions for you. The survey answers are measured on a scale of 1 to 5, 5 representing outstanding and 1 representing poor. And now I'd like to pass this over to our trainer to present today's topic. Hey, Francisco, thank you so much for joining us today.
Um, Thank you, Tracy. Hi, everyone. Welcome to our training today, BigQuery 2026 on Google Cloud Performance, Cost, and AI Readiness. My name is Francisco Quintana, and I will be your instructor for today. My background is actually in data engineering and machine learning. I am a Google certified data engineer and machine learning engineer, and I've actually worked with Google back in 2023 and 2024 to create the generative AI content for their Google Cloud courses. So today, my aim is to help you understand how to use BigQuery in terms of efficiency for any SQL tasks you might have, and also use BigQuery for its AI capabilities, because BigQuery is no longer just a SQL solution, it is actually an AI solution as well. So let's get started. Now, on our agenda today, we're going to cover an introduction to BigQuery and how BigQuery works. We're also going to get a very good understanding of how BigQuery applies to modern data and analytics teams. After that, we're going to be looking at measuring business impact with BigQuery, analyzing a few use cases across different industries in BigQuery. And then we'll be looking at how to optimize BigQuery for performance and cost efficiency. And then we'll finalize with getting started with BigQuery for building AI solutions responsibly and knowing how to scale those solutions as well. And finally, we'll summarize with our course with the final few slides. So that being said, let's get started with our first piece of content today. So today, we aren't just looking at BigQuery as a database, but as a data intelligence platform. BigQuery is unique because it separates storage from compute. This means it can scale infinitely without you ever having to provision a single server. In this session, we're going to move from basic SQL execution into advanced cost-saving maneuvers and building machine learning models directly within the BigQuery console. So our goal in this session is to make your queries faster, your bills smaller, your data smarter, and your AI more capable. So let's get started with the rest of our content. Now, let's talk about what is BigQuery. So when we're thinking about BigQuery, you need to forget about traditional relationship databases because BigQuery is cloud native. So what exactly do we mean by cloud native? Well, it means that it can handle replication, durability, and scaling without you having to manage those responsibilities. So Google will take care of the replication element, the durability element, and the scaling element. That means that you can just focus on writing efficient queries and making sure your data is up to scratch. We're going to talk about something else called Omni later, or BigQuery Omni, which is an ability to use BigQuery across omni channels, so not just digital data sources, but off digital data sources. We will also look at how to query data with solutions like AWS S3 and Azure Blob Storage without having to take it out of AWS S3 or Azure Blob Storage. But of course, we'll also focus on the BigQuery engine that powers BigQuery. And just for you to know, BigQuery is actually a key tool inside Google's products. Quite a lot of products actually do use BigQuery as their main processing technology. So how does BigQuery work? What is the secret behind BigQuery? Well, if we think about most databases, they have a storage and compute element. If you have more storage, you more likely need to buy more compute. They're almost one in hand, right? You buy a server, and that server has a storage element and a compute element. What BigQuery does is that it decouples them for you. Your data sits in BigQuery's custom storage solution, which is called Colossus. And when you execute a query, it uses its analytical engine, which is called Dremel, to give you the computing power you need. Now, as I mentioned in earlier slide, you don't actually have to set how many compute resources or how many CPUs you need. Google will automatically determine that. Google determines this by using a custom algorithm in Dremel. Now, how do storage and compute work? Well, they actually work with a network called Jupyter. Jupyter is the in-between layer that tells the analytical engine what data to get from storage, and it tells the storage engine, Colossus, what data the analytical engine, Dremel, needs. And it can do this in just a matter of milliseconds. So this separation is why BigQuery is so cost effective, because rather than paying for a single server that does both things and you have to optimize that server for it, Google sets up their storage system to be optimized for holding data storage, their analytical engine to be optimized for large scale data processing, and their networking tool to optimize communication between those. So each of them is treated kind of like their separate product, and together they make up BigQuery. So let's talk a little bit about how the storage works. Now, BigQuery is what we call columnar databases or columnar data power. What we mean by this is that each column is its own file in BigQuery's storage system, which again is called Colossus. This is unlike most transactional databases that use row-oriented storage. So if you wanted to calculate the average price of a product in a row-based system, you have to read all the other columns like product ID, description, and date just to get the price. But BigQuery uses columnar storage. So if you just want to see the price of the product in just a price column, it will just select the price column without having to go through any of the other columns. The unique columnar format that BigQuery uses for this is called the capacitor. So what it does is that it puts the column data for price in one single file in Colossus. So you're only ever communicating with that file. If you've ever used BigQuery before, you will notice that BigQuery actually charges you less the fewer columns you use, unlike row-based systems. So this is what gives BigQuery its fast read capabilities when it's getting data from storage. Now let's talk about the Dremel engine. Dremel is the brains, the analytical power of BigQuery. It's the CPU that gives us the capability to use BigQuery. Dremel works with a tree execution system. So what do we mean by this? What we mean is that each CPU is known as a slot, so I'll just refer to them as a slot, is actually a different node in your analytical engine. So for example, let's say I want to read 10 gigabytes of data. Well, Dremel will say, okay, I need 10 CPUs. But maybe to read all those 10 gigabytes of data, it doesn't need to use all 10 CPUs at once. It might say, okay, just to get the first input of data in, I just need 2 CPUs. Okay, now I need to do a complex calculation, like let's say an analytical function, right? Like a window partition with a sum function attached to it. It might say, okay, now I need to branch off to 3 CPUs to process the rest of it. And as the query goes on in different stages, the tree grows up to the 10 compute nodes. So what it has is what we would call leaf nodes. And just like a leaf in a branch, where that you could have one leaf at the very beginning and then several leaves at the end, it will essentially follow this approach. Now, it doesn't necessarily mean that it will always grow from 1 to 10 nodes. It could be the opposite. It could start with 10 and scale down to 1. One of the great things about the Dremel engine that BigQuery gives us is that if you use the on-demand pricing model, you automatically get 2,000 compute nodes. 2,000 computers working on your query. Now you can actually get more, but then you would use the fixed price modeling. And we'll talk about pricing later. But the way the Dremel engine looks at it is says, I'm going to take the data that you gave me. I'm going to estimate how much compute power I need. I'm going to estimate that maybe I need 10. And through different stages of working with that data, from read, transformations, analytical functions, and finally writing the data, it might go between 1 and 10 nodes. So that's how the Dremel engine works. Now let's dive a little bit deeper into how the query processing steps work. So when you want to execute a query, use your typical select from clauses, right? So let's say you select 5 columns. What the query will do is it will call these 5 columns from Colossus. Colossus will then pass them to Dremel so it can do the processing. The first step is to analyze the query. So as you write your query, you'll say, okay, based on this query and the work you need me to do, I might need 100 compute nodes, right? Then it will execute a plan. So it will create an execution plan saying, okay, I probably should start with 20 because it looks like I'm going to need to read a lot of data and then scale up to 100 when I'm processing. And maybe I just need 2 at the end to write it. So this plan will be the tree of execution. Based on what stage of your query needs how much compute power, the slots, which is the compute nodes, will then be allocated on demand basis. It can also do parallel processing. So let's say, for example, you're reading a large file. That file doesn't have to be read with a single compute node or slot. It can actually be broken across 2 or 3. So what would be happening is that you would have that file being processed in 2 different tree branches, if you will, simultaneously. That way it gives you that speed advantage that other solutions don't get you because you're doing parallel processing. And that gives BigQuery one of the fastest performances when it comes to SQL writing. In fact, BigQuery can read 1 billion rows of data in potentially under 5 seconds. Now, let's dive a little bit deeper into what is actually happening at this stage. One of the hardest things to do for any distributed database is a join function. Why? Because joins require matching the data using a common key and different systems. So in this case, what we would do is that we will actually take advantage of BigQuery. What BigQuery will do is if when you're doing a join, let's say with table A and table B, it will allocate a number of slots. And it'll say, okay, table A, we're going to work with 1 slot, so 1 compute node, table B with 100 compute nodes. They will communicate to each other through something we call the shuffle layer. The shuffle layer is actually going to pass information to both those tables saying, okay, this is our join key. I see that I have some duplication here. Maybe I need to do a deduplication step. So what it's going to do then, as it's going through a shuffle layer, is it's actually going to write them to an intermediate data disk. This intermediate data disk will store the data temporarily. So in case it ever needs to read from table A again, it doesn't have to read from the location table A. It can just store them and read it from that in-between layer. The slots then shuffle the data through each layer until your query gets completed. So as BigQuery is performing your join, it's actually reorganizing your data to be optimal for that join. So what's happening is if table A is sitting in a certain compute area or certain storage area and table B is sitting in a certain storage area, they'll be processed together with an intermediate storage area to make the join faster. So it's shuffling the data through that intermediate shuffle layer, putting it all together, and then finally it starts to join the data into one final table. The reason BigQuery can do this so fast is through its Jupyter network that can handle petabytes of data. So it's significantly faster than any local disk drive you might have, or even any on-prem Hadoop or Spark cluster you might have. And remember what I said earlier, you get up to 2,000 slots or compute nodes on the on-demand level. And then, of course, if you use the fixed price level, you can technically buy more than 2,000. So we now understand that inside here, we're looking to see how we can improve our query. Now, to get query speed working well, what we want to use is that we want to use performance optimization. Performance optimization occurs when we're using partitioning and cluster tables. We're going to cover this in more detail in just a little bit. We're also going to talk about how to optimize the cost because there's not much value in optimizing performance if we're going to pay astronomical rates. We want to optimize the storage costs while optimizing the performance of our query. So a couple of things to remember is that we always want to process the minimum amount of data needed to execute. We never want to use a select star to read all columns if we don't need to use all columns. So we want to optimize the data the best we can. Now, before we go into more detail about performance, let's actually talk about partitioning. What is partitioning? Partitioning is when we actually break up our data using a sort of integer or time-based column. Before we go into more detail about partitioning, let's talk about the benefits of it. Let's say, for example, I have a query that I'm executing, and I want to see the average sales growth for the past year. If my data is not partitioned, my January data might sit next to my September data, because what's actually happening is that my data is not organized. But if I partition by timestamp, so when the data was created, then my January data will sit next to my February data. So January 1st will be next to January 2nd, January 3rd, and such if it's partitioned. If it's non-partitioned, potentially January 1st might sit next to March 11th. And then when you're trying to say, hey, what was my average growth? And you're doing an order by based on time, it will actually take longer. But on a partition table, it'll be faster. So how does this partition work? Well, we actually use a time-based column or integer-based column to partition. The most common way of doing it is using a time-based column. So usually it's the time the data field was created. So let's say when the transaction happened, or it could be the time when the data was ingested, or you can just create a unique integer number, but usually a time-based column works best. Then once you select your time-based column, say you select a date column, then you use the partition time to let the BigQuery know this is my time-based column. So if you use a date column, let's just say date like year, month, day. What will happen now in BigQuery is BigQuery will organize the data based on year, month, day, usually ascending order. So January 1st will always be before March 11th. So it will organize the data in Colossus in ascending order. So your January data is always next to your March data. The other benefit of this is because now when you run your query, it will only match that partition. So on a partition table, if I say I want to see all data between January 1st and March 11th, all that data is next to each other and it will read it in that order. In a non-partition table, potentially January 1st might be next to December 10th. March 11th might be next to November 27th. And what's going to happen is that it's got to read all the data first, then order it. But in a partition table, it's already pre-ordered based on the date timestamp. Now, in BigQuery, you are allowed to do 4,000 partitions per table for the most efficient performance. So what do we mean by that? That means all the tables in your project can have up to 4,000 partitions. So if you needed to have 4,000 tables with a unique partition timestamp, or you can partition on two date-based columns or integer-based columns, then you can do it approximately 4,000 times per your project. There are ways to exceed these limits, and these limits do always change on a monthly basis, depending on what Google decides to do there. So that's partitioning, organizing our data using some sort of integer or time-based timestamp where all the data is together based on that integer or that time. Usually time-based like date or timestamps are the best ones. Now let's talk about something else called clustering. What is clustering? Clustering is when we organize the data based on specific columns values. So what do I mean by this per se? Well, let's assume that I'm always querying the same product, right? So let's just call it product A, product B, and product C. I'm always querying those same products. If I have a non-clustered table, product C might be next to product Y, right? Because it's non-clustered. There's no order to it. But if I tell BigQuery that I want to use cluster columns and I say the product name, so product name would be clustered, and I'm always using product A, B, and C, what BigQuery is going to learn is saying, okay, since Francisco's always using product A, B, and C in his queries, I'm going to group them together in Colossus. So what will naturally happen is that BigQuery will move product C next to the product B data and next to the product A data. Let's say 6 months pass, and now I'm always querying product A, Y, and Z. Then what will happen is BigQuery will notice this pattern and say, okay, let me put product A's data, product Y's data, and product Z's data together because these seems to be the most popular products that are being queried. So that allows for faster read operations. So BigQuery using clustering will automatically change how that underlying data sits in Colossus to make it faster for you to read and write to. Now, what are some popular columns to use for clustering? Well, one of the most popular ones is usually columns with high cardinality. So like ID columns like user ID. Product name columns are actually pretty good. Product ID columns, city names. Usually I say the best practice when it comes to selecting your cluster columns, and I think BigQuery allows you up to 5, but this can always change, cluster columns, is usually what am I filtering out by the most? So when I'm running my queries, I always think, am I filtering out most by this column or that column? So whatever I'm filtering out the most, that's usually a good indicator of what should be your cluster column. Now, on a good news is you can always change your cluster column if you did not, if time requires you to change it, or maybe you've noticed that your original clustering is not the most optimal. Partitioning, however, is a little bit different. Partitioning, usually once you partition that table, it's extremely difficult to switch your partition around, but not impossible. Clustering is a lot easier because it will naturally update the cluster columns based on usage if you selected those cluster columns. You can always add a new one later, but usually your limit is approximately 5. Another way to optimize our querying is by using materialized views. Materialized views are like cached queries that stay fresh. So let's look at an example. Let's assume I have a dashboard that calculates daily sales. Well, every time someone refreshes that dashboard, I don't want to rescan millions of rows of data. Instead, if I use a materialized view, it will only query the data that is necessary. So how does it do this? Well, once the user queries the original base table, the materialized view will start to see what fields, columns, date for timestamps, because you would have partitioned your table ideally before or clustered it, and it will start to load that data ahead of time. So for example, if I'm doing daily sales, it probably might say, okay, I always see that you're doing 3 months daily sales. So what I'm going to do is I'm just going to have that preloaded in a cache query. So instead of executing the query from scratch in a materialized view, it would have already been preloaded because it would pick up on patterns. So materialized views look to optimize the data in the background to make sure that data actually is efficient and works well. So that's one of the benefits of using a materialized view. In the background, what is actually happening is that it will start to reorganize the table in Colossus, save the pre-computed results in a cache query, if you will, and then you're just querying that view. Now remember, your materialized view is always querying your source table, right? So a table that feeds into that view. So at times, you might need to refresh the materialized view to let it get the latest data from that source table. The good news is BigQuery can automatically do this for you because materialized views can be automatically refreshed on a schedule that you'd set. So you could do it every 5 days, every 5 minutes, every 5 weeks, up to you, or allow BigQuery to do it based on when that table has been updated. My personal recommendation is that you set your materialized view refresh schedule because you might not always need to update the materialized view when the data has been modified and such, because sometimes you're just doing a little bit of old data clean, so you don't need to re-up the view. However, materialized views are essentially cached queries that allow you to run faster. It's very useful when you have your view connected to a dashboard, and you will actually notice between using a normal table and a materialized view in a dashboard that the dashboard should be significantly faster. So if your base table takes a minute, your materialized view might just take 10 seconds. Highly recommended to use materialized views. So BigQuery was originally built for Google search processing. So when you were writing a query or a search in Google search, BigQuery was actually built to understand the query and show you the result quickly, right? Now imagine how many searches are being executed per day. probably billions of searches per day. So Google needed a fast solution that could process those searches quickly and show you your results quickly. And it actually used BigQuery to achieve this. So BigQuery can look at structured and semi-structured data. So as long as it's text-based or numeric-based, BigQuery can understand it. So let's look at an example of this. Let's assume I need to search for a specific error code in a 50 terabyte log table, which means I need to do a full scan. Even if I cluster and I use something like percentage error 404, searching for that, it can be slow and expensive. Now, BigQuery actually has something called BigQuery search indexes. What it does is that you create an index in a column, and BigQuery builds what we would call an inverted index, or a map to every word and its location in storage. Now, when we use the search function in BigQuery, BigQuery goes straight to the data without having to scan the whole column. It's essentially bringing Google search speed to your SQL table. This is a game changer for people that need to search large amounts of data like security teams. For example, let's say you need to look for a specific address. Well, that specific address has already been mapped to a location in data storage. So BigQuery knows that once you put that specific address in, like a dictionary or a map, it'll say, okay, this is in this location of data storage. So I'm just going to go straight there rather than having to look at the whole column. We call this fast text lookups using inverted indexes in BigQuery via the BigQuery search index function, which you can see there, the search function. So it's kind of like and a regex query, but faster and more efficient because you would have pre-mapped the data ahead of time. Now, we'll get into it in more detail a little bit later, but in the world of artificial intelligence, one of the most popular methods of searching for data is using RAG databases. And these RAG databases usually include some sort of vector search or vector database, like embedding models, right? Now, one of the great things about BigQuery is that BigQuery is built to handle modern AI. And just like a database, a RAG database is just a standard database, BigQuery can process this. BigQuery has what we would call a vector index. It means that you can store data in a vector database and perform vector searches with that database being BigQuery. So let's say that you want to apply BigQuery to your LLM and have it behave as your vector database. Well, BigQuery will store all that textual data in numerical representations called embeddings, and then it will use a vector index to search not just for the exact word, but for the meaning. So if you have a column of product descriptions and you convert it to embeddings, the vector index search will allow you to ask, let's find products similar to this image or this description. And by using the vector inverted file index, BigQuery can then group similar vectors together. So when you query, it will only search the most relevant groups. This is the core technology behind the recommendation engine and how we feed relevant context to large language models like Gemini, which is Google's AI model. So BigQuery actually has constructed itself to also allow us to search for data that could be in the form of documents, text, or standard structured tables for large language models like Gemini and other models like Anthropic or GPT-based models. And it uses these fields, it uses this technology, vector search, to perform those executions very quickly and accurately. Okay, cool, ready. So we've seen how BigQuery can optimize storage using material views, clustering, and partitioning. But we also need to think about when we execute a query, how can we make that query more efficient? This is done through the query execution plan. So in every BigQuery console, we have a tab called execution details or graph execution details, depending on which version of the console you're using. And what it will do is that it will show you all the stages of your query, from the first read stage to the final write stage, and in between any middle stage like a join stage, an analytics, a partition stage, a aggregation stage, and such. What this gives us is a detailed overview of which stage is taking the longest. So say, for example, our join stage is taking a long time. It's using a lot of computational power to execute that join. How do we fix this? Well, the query execution plan will tell you what are their hot zones or the delays in the join. It might be that it's taking a long time to join the data with a single common key. It might be because there's a lot of duplications. It might be because I had to shard it multiple times, which usually indicates that it's trying to join too much data at once. So then you could take that information and say, okay, if there's a lot of duplication, maybe in the previous stage, I should remove all duplication. If it's taking a long time with the sharding, it might say that might be too much data or too much too many columns in the first join. Maybe I need to limit this join a little bit by either doing a smaller window or potentially removing some columns that are not necessary, or potentially maybe making a better join key. Maybe the join key you're using is going to be a many-to-many join, and you should use a one-to-one join. So maybe you want to make your own custom join key or join on more than one column. So the query plan is going to break up each stage and tell you what is taking the longest. And in today's world of artificial intelligence, it can actually even tell you how to improve your query. It might actually say, hey, here you should add another column to join it with. I suggest this column. So the query execution plan is available in the BigQuery console, but it's also available if you use the command line interface or the Google Cloud API to connect to BigQuery or the SDK. So it's not just a user interface to the BigQuery console. It is available to you across the different ways you can interact with BigQuery. Now, of course, if you use the console, it generates a very beautiful looking graph that's easy to understand. If you're using the API and such, it won't generate that graph by default. You would need to generate it yourself. So the console is actually a pretty good tool to use, but you, of course, can use other tools as well. And it'll still give you the same query execution plan, but it'll look more text-based. But there are ways to graph it using the BigQuery API. So now let's discuss how we can improve our query. We already know our query execution plan will tell us what's going on, but we can also use some additional information to help us identify bottlenecks because metrics tell the story. So for example, besides just having your graph created and your query execution plan, you also get execution details, which tells you how much time it spent before it executed the query. It also tells you how much slot time you were using. So let's talk about slot time and exactly what that means here. Remember that I told you a slot is essentially a compute node that you use to execute BigQuery, right? So with a slot, you might use 5 hours of slot time, even though your query might just take 30 seconds, because what that means is that it took approximately 5 hours of all the 2,000 machines BigQuery gives you on demand to execute your query in 30 seconds. This is actually very powerful and useful because then you can see how much computational time you're using for your query versus how much time it took you to get the results. And from here, you can identify bottlenecks. So your BigQuery console and in the query execution plan will tell you, hey, I had to use 3 hours of slot time just for this join, which tells you a lot of computational effort was used for that particular join, even though it gave you the result in just 10 seconds. This is where you can say, well, maybe 5 hours of slot time is too much in this join. So maybe I should break up this query into smaller pieces. So maybe you're querying 20 terabytes of data in a single query. And maybe you need to say, you know what, I need to break this up into 4 queries of 5 terabytes each to make it more efficient. And it might still take 10 seconds, but use less computational resource. Now, it's very important you understand that slot time is used across everyone in your project. So let's say you're not the only person using BigQuery. If you're taking up 5 hours of slot time, hence a lot of computational resources, that's less resources than your other teammates can do or other dashboards that are using BigQuery can use and such. So you really need to think about how much computational resource should I be using to execute this query. And BigQuery helps you calculate this by looking at the data plan, the execution details, and it'll identify where your data is where your data is creating skews, causing one worker to spend too much time on it. It's also important to understand that if you are using the on-demand pricing, that your compute time is actually going to be based on how many people in the region are using BigQuery. So for example, if you're using BigQuery in a certain region of the world, like a specific region of the world, which BigQuery will give you a rough idea of what region of the world you're using, that region might be using a lot of computational time. So you do have 2,000 compute nodes to yourself, but everybody is using Colossus worldwide in that region. Now, if you have a large team, everybody's going to be sharing those 2,000 compute nodes. So you need to be constantly thinking about how do I identify what areas of my query are taking the longest to free up compute nodes for everybody else and make sure that everybody can actually run their queries without waiting long. Now, to tell you the truth, in my experience, I've never had to wait longer than 60 seconds for a query to execute. So generally, it's not really a problem. But when you're across larger data teams or you're building very production quality systems, you really do need to think about identifying these bottlenecks by looking at the execution details, looking how long it took for your query to execute versus how much slots. Because BigQuery does have the model called double the data doesn't mean double the time. So it will still give you the query results fast, but it might take double the slot or computational power. And you never always want to be doubling your computational power. You want to see how you can break up that query to make it more efficient. So when you're trying to optimize your query, you need to think about what can I optimize. So remember, if your query is running slow, first check, are you using partitioning columns? Then check, am I using cluster columns? Am I using a combination of both? If I'm using non-numerical data, and I'm using mostly text-based data, right? Then I might think of am I using the search or vector indexes correctly? If I am doing all those things, I might need to look at my query plan to find where am I taking the longest? What areas am I actually using the most computational resources? Then think, do I need to fix my underlying data using some of the tools like partitioning and clustering or materialized views? Or do I need to think about how I execute my queries more efficiently? For example, the with statement in BigQuery, though it's very elegant to use and makes it very easy to write queries, is actually computationally expensive. A with statement will take a lot longer to execute than saving a temporary table, for example. So again, all this would be available in your query execution plan, and from there you can actually start to improve your query as best as possible. So now what we're going to do is we're going to jump into cost management. Because a lot of the things I told you about improving query performance can actually also be used to improve your querying cost and your data storage costs. Let's take a quick 5-minute break, and then I'll start on the remaining topics after this break.
Sure, we are now going to take a 5-minute break, but before we do that, we are going to launch a quick poll that we want to invite you to participate in. Doing so helps us know how we can better serve you by telling us who might be interested in more information or in taking some additional training. In addition, we have a lot more informative webinars coming up, so please go to netcomlearning.com/webinars in order to register.
Welcome back, everyone. Let's continue from where we left off. So previously, we were talking about how to optimize querying performance and such. But now what we want to look is how to optimize cost management. Now, with cost management, we're going to see similar steps, but now we're going to focus on how those steps impact our querying costs and our data storage costs. So let's dive into this. Now, in BigQuery, as I mentioned, when it comes to the analytical engine, you have two types of pricing models. The first price model is what we would call on demand. So you don't pay a flat rate fee, you charge per what you use. So for example, if you don't use BigQuery for 2 weeks, you don't pay for those 2 weeks. Now it's priced per size of the data that you query. So for example, if I query 1 terabyte of data, that is approximately $6.25 US. Now prices do change, so always do check your prices, but it is approximately $6.25 US. So if I were to query 1 terabyte data a month, I only pay $6.25 US. The good news about BigQuery is that in on-demand pricing, you get the first 10 gigabytes free. So the first 10 gigabytes are free, and that renews every month. So this is on-demand pricing. On-demand pricing is great when you're not using BigQuery heavily. Now, this pricing is only related to the analytical engine, so Dremel. This is only related to Dremel, where you just use the on-demand pricing. This is not related to storage pricing. We'll talk about that a little bit later. Now, what happens if you don't want to use on-demand? For example, let's say that you're using on-demand pricing and you're spending approximately $50,000 US per month in on-demand pricing. Well, you could probably get the same performance for $25,000 a month less. How is this done? Well, you have different fixed priced options. Some of those fixed price options could be editions. Some of those could be enterprise or enterprise plus. So how does fixed price pricing work? Fixed price pricing work. It works in this way. I would make an arrangement with Google using the BigQuery platform saying, I will pay for, let's say, approximately 1,000 slots for a month at $5,000 a month. So even if I don't use all 1,000 slots that month, I will still pay a flat 1,000. But in on-demand pricing, you can use 1,000 slots a month and still go over $5,000 by a lot. Because again, it's just looking at data size. With the fixed rate pricing now, I can query 100 terabytes of data. 100 terabytes of data, and Google can only charge me a maximum of $5,000 a month. With fixed rate pricing, you'll have different options like standard, enterprise, and enterprise plus. Essentially, they're just other levels of the pricing model where the higher you go, the better deals you'll get, but it means a more long term. So for example, if you use the standard pricing model for fixed price, you might get $5,000 a month and that rolls over every month. But if you go enterprise and enterprise plus, what might happen is that Google will say, okay, we're going to give you those 1,000 slots that you requested for per month, but we're going to give it to you at $1,000 a month, but you need to commit to a 5-year contract. Now, usually the contracts are not that long, but you can get it up to 5 years. Usually it's done at a yearly level. So that is the benefit of it because now you can save a lot of costs. Now, what would happen in fixed rate pricing if you need more than 1,000 slots? So what if you're saying 1,000 slots is not enough for me to operate here? I need 2,000. Well, the good news is Google can actually give you those additional 1,000 slots to your pricing model relatively quickly. You might actually even have it ready within 5 to 10 minutes. So it's actually really impressive of how fast it can do it. So if you realize that 1,000 slots is hitting your limit and you're not being able to query as fast as you want, you can upgrade to an additional 1,000 almost immediately. Now, if you want to upgrade to 20,000, that might take a little bit longer because you would put the request through, and usually that request will take about a day, maybe a little bit longer to approve. However, what if you want to do the reverse? What if you did a year commitment at $1,000 a month for 1,000 slots, and now you said, hey, I don't need the all 1,000. It's 3 months in. I want to lower it to 500. That is still possible, but it's less direct. That usually means that you'll need to enter a conversation with your Google Tech partner or lead or with your Google sales rep and discuss it. It is possible, but it will not be as easy as it is to upgrade. So you have fixed price and on demand. My personal recommendation is if you're relatively new to BigQuery, try to continue using on-demand pricing until you have approximately 1 month of data to compare your on-demand usage before you commit to fixed pricing. Fixed pricing sounds very, very expensive. However, it can actually be cheaper if you're a heavy BigQuery user. So my recommendation is use on demand for a while, identify your pricing models, and then your price limits and floors, and then from there, increase it. Now, another piece of advice I would give is that because in BigQuery, it works at a project, you can have one project that's on demand and one project that's fixed. And what this will allow you to do is say, okay, I want to use my fixed price project right now. I've hit the limit for my fixed price project at the current moment, but I know this limit is only temporary. Why don't I use my on demand to cover the remainder? And maybe you're on demand, you spend less than $100 a month, and your fixed pricing, you spend $1,000 a month. You can easily switch between the two. And you can query data inside different projects, providing that your service account or your email address that you're using has access to both projects. So that would be one of my recommendations as well. Have a on-demand project and a fixed price project in case you ever do need a little additional help temporarily. And that way you don't have to increase your BigQuery cost by adding an additional 1,000 slots when you only need them for another month. Now, that's how the pricing model works for the Dremel engine. Let's now talk about how we lower costs overall. So let's just assume that we're using on demand, right? And we know that each terabyte of data cost us about $6.25 US. Now, how do we make sure that we keep it as low as possible for using on demand? Well, one, the more data you query, the more expensive. So it's not so much the number of rows, it's the number of columns. So if I query 10 columns from the same table, it'll be more expensive than querying 5 columns. This is why we don't recommend using a select star approach. A select star approach, what it does is that it says, I want to query all the columns, so that's more data that you need to query. So we only query the columns that are necessary. Another piece of advice is to only use partition tables when possible. So if you do have a table that has a date timestamp or some sort of integer-based column that allows you to partition by it, I recommend using it. Because let's say I have a whole year's worth of data. If I have a non-partition table and I want to just get the data from January, then I will actually read the whole table. So I'm actually reading the entire table. But if I have a partition column and I say I only want the data from January because I timestamp partitioned it, it will only read the subset of data. So let's assume that my whole year's data is 10 gigabytes. Let's assume my January data is only 1 gigabyte. If it's a non-partition column, you're going to be charged 10 gigabytes no matter what. But if it is a partition column and you just want to see the January data, then it will only look at the January data for you. So this is what I highly recommend using partition tables. So we know partition tables gives us a speed advantage, but they can also give us a cost advantage as well. So again, highly recommended to use partition tables. Now, what are some other things that we can use to improve on it as well? Well, BigQuery actually has a physical storage billing model. So let's talk about this. BigQuery actually has to store your data, right? And it has two options of storing the data. It has active storage and long-term storage. What is active storage? Active storage is essentially when that data is being queried or modified roughly more than twice a month. So if I'm querying the same data, let's say the same January data more than twice a month, it's in active storage. In active storage, it's approximately 0.002 cents US per gigabyte of data. But in long-term storage, and I'll explain what long-term storage is in just a second, it is approximately half that price. So what is long-term storage? Well, BigQuery will notice, are you querying the data less than once a month? If it notices this pattern, it will say, you know what, I'm going to move you to the cheaper storage model or the long-term storage model. There's no performance degradation. Your queries will still run as fast, whether active storage or long-term storage. But what BigQuery is saying, hey, if you're not using this data frequently, I shouldn't be billing you frequently. So you have active storage, which is a higher pricing model per gigabyte of data per month, and long-term storage, which is about half the price of active storage per gigabyte of data per month. So active storage is more expensive. Long-term storage is cheaper, to keep it simple. BigQuery will automatically look at your usage and determine, should I move this data to long-term storage and active storage? It will look at this based on the data's usage pattern. So again, if you're always querying the January month, it will very likely stay in active storage. But if it's not, you're not querying or modifying that month of data, then very likely you'll move it to long-term storage. And it can easily switch between back and forth. So it can move between long-term and active, active and long-term, and then back to long-term. It can always switch based on your behavior patterns. Usually BigQuery waits about somewhere between 10 and 30 days before it makes a decision, because generally rule of thumb is if the data hasn't been used or modified in any way for at least 30 days, it will very likely move to long-term storage. So remember, we have two ways of getting built in BigQuery. We have being queried using the Dremel engine, so the analytical engine, so on the size of your data, and of course your BigQuery storage model where your data is stored. Another piece of advice that we give to lower costs is set expiration dates for your tables. What do we mean by this? Well, we mean that if you have a table, let's say sales per month every year, and it's been 5 years and you're not really using that table anymore, you can set an expiration time saying if this table hasn't been used for 5 years, it's a bit of an extreme, but for let's say 5 years, it will automatically delete that table. Hence, you're not paying the storage model. We don't really cover it in today's session, but there are cheaper ways of storing data long-term if you don't plan to use it outside of BigQuery. And again, if you're not going to use the data in BigQuery, you might as well not pay the BigQuery storage pricing and move it somewhere else like Google Cloud Storage. My recommended approach because it offers cheaper storage solutions. Finally, you can use something called information schema. What information schema does is that it gives you information on your data storage and your query usage. So it might tell you, hey, this query is actually quite expensive. And again, as I said earlier, in the world of artificial intelligence, what it might do is say, oh, actually, you know what I'm going to do? I'm actually going to lower this query's cost by making these suggestions for you. And once it makes those suggestions, you can choose to apply them if you want and fix them. But it might not always need to use AI. You can just run the information schema command, and the information schema command might tell you exactly how to improve this query. So how do we know how much data we need if particularly we want to move to a fixed price model? Well, generally, the best approach is to use the previous performance of BigQuery. The great news about BigQuery is that all your queries and historical performance is actually recorded in in Google Cloud Logging and Google Cloud Monitoring. So you can analyze your slot usage and query demand and then determine saying, well, I've noticed that I've never used more than 200 slots per month. If I want to move to a fixed pricing model, let me purchase 400 slots per month just to get a little bit of buffer, just in case. And using that buffer, you can do it. BigQuery and Google Cloud also have what-if scenario planning in your financial billing option. So it can say, hey, you might get a massive spike of data, or you might get a massive query usage over the next couple of months, and this is what it would look like. So again, it helps you plan out a little bit better. So there is what-if scenario planning. Probably one of the best things to do is use the monitoring tool's visualization. The monitoring tool will visualize your BigQuery capacity, your query latency, your dataset usage, your storage usage, and then plot out some very useful charts to determine what is the best use of BigQuery in this case. And of course, one of the best things to do is to just use BigQuery for a bit of time, wait to see if trends stay the same, and then determine if you need to increase or decrease your capacity. But as I said in an earlier slide, I highly recommend that you have a on-demand project and a fixed price project. That way, if you think you might need to increase your BigQuery usage temporarily, you can just offload that to your on-demand project rather than having to commit to a even monthly increase in your storage, in your fixed price costs. So these are how we can plan our capacity planning. Now, I'll give you a little hint. Actually, now with Gemini being incorporated into BigQuery, you can actually ask Gemini, do I need to increase my slot usage or decrease it? And it can actually analyze it for you and give you recommendations if you should or you shouldn't. So earlier I was talking about pricing additions. So let's dive into these in a little bit more detail. So as I said, you have standard, enterprise, and enterprise plus edition. So these are our fixed flat rate models pricing, right? So standard is what we would call our entry level fixed price model. It gives you the power to query on BigQuery at a low cost floor. So this is pretty good if you're just doing it for experimentation and you need fixed price, or it's a relatively small data operation. Enterprise is very likely where corporations would be using this data. Not only does it give you slightly better pricing for long-term usage because you're committing to longer-term plans, but it also gives you the ability to add virtual private centers for service control, meaning that only certain people that are active to your virtual private center can access your BigQuery data. This gives you a huge security boost because even if someone got inappropriate access to your BigQuery through nefarious means, they still will not be able to use it unless they're part of that VPC service control. So this gives you a high degree of security. Enterprise model also comes with materialized views pricing. So it might give you better pricing for using your materialized views. Then, of course, we have Enterprise Plus, which is essentially giving us the best possible performance with the latest advanced security features such as customer managed encryption keys that can be easily applied and better pricing. So here now you're getting probably the full package. Of course, probably is paying a little bit more, but for what you're getting back in terms of long-term usage, it's actually great. So your fixed price models are standard, enterprise, enterprise plus, and then of course you have your on-demand pricing model. My recommendation is always start small and scale up. In Google Cloud, it's usually pretty easy to increase your addition if you want versus decreasing it. So usually take some time, figure out, and even if you realize that you need more, it's actually relatively easy to increase it because it's just going through the interface and adding one or two requests to get your data increased. So these are our enterprise storage solutions, our standard storage solutions, and of course our on-demand, pricing solutions. I take that back, pricing solutions. Now, you can actually control how much is used across projects or team members. How do we do this? Well, BigQuery has something called capacity management. So let's say I buy 1,000 slots. Well, I don't want just anybody to use those 1,000 slots. Let's assume I have two workloads. One workload is for my data science work, and another workload is for my data engineering work. Let's assume that data engineering workload is business critical because it powers my ML models with the data and it powers my dashboards that are used by C-suite individuals. So if I have 1,000 slots, I got a great deal from Google to do 1,000 slots. What can I do? Well, I can reserve some of those slots. I can say, you know what? For my data engineering workload, I'm going to reserve 700 slots. For everything else, the remaining 300 slots has to be shared equally. So you can do capacity management reservations based on needs. Quite often, a very popular one is that you have a prod, UAT, and dev environment, and out of those 1,000 slots, you divide it evenly. Or very likely, your dev environment will have fewer slots because it's just a dev environment. Your UAT environment will be a little bit closer to your prod environment, and your prod environment will be pretty much your highest slot usage because that's the one that needs to work. That's actually quite a good option. Now, one of the great things about BigQuery is that let's assume one of your environments needs more usage. Well, BigQuery is actually smart enough to say, oh, let me move some of this usage over to another environment because I see you're not using this one. Capacity management reservation can also be done at the user level. You can actually say these users can only use these slots at this time versus other users. So that way you can maybe let your senior team get more usage or your junior team get more usage based on your requirements for that particular project. So you can control access based on the project it's in and say, okay, this project should get the most because it's the more business critical one, or you can control access based on users or even time of day. My personal recommendation is probably you want to give control at a project level. So you want to create like a production project or identify where are your business critical projects and then save your slots for that entire project and then say, okay, these one will get there. If you do not allocate slots across the projects evenly, don't worry, BigQuery will take care of that for you. BigQuery is actually pretty smart and it'll do a fair balancing approach where not one query by one user or one project will get preferential treatment. It will actually try its best to give a fair balancing. So let's assume someone executes 3 queries at the same time, each across different project, across different tables. Out of 1,000 slots, BigQuery will then do 333 per query because they'll do it evenly. But of course, if you use capacity management reservations, you can say, hey, these queries on these projects always take the highest level of importance. So then maybe out of those 1,000 slots, 700 will be dedicated to just that query in that project alone, and the remainder will be split evenly across the remaining projects and queries. It doesn't have to be long-term. It can actually be temporary when you're doing this. Now let's actually talk a little bit about fixed pricing and how maybe I can get fixed pricing without having a long-term commitment. So there's something known as flex slots. So these are fixed price, but you're not doing such a long-term commitment. Because let's say, for example, I need for sure that I need 5,000 slots, but I've only bought 500 for my year commitment. So I need those 5,000. Yes, I can maybe tell Google, hey, I need these 5,000 for 1 month or 2 months, and then I need to downgrade. But that's a little bit inefficient and a lot of conversations to have. Perhaps what I can do is I can just use the slots temporarily or flex those slots. So what flex slots do is that they give you dedicated resources, not on demand, which is based on if the demand's available, but dedicated resources for a small period of time. Now, you pay a slightly higher rate per second, but you don't keep these slots long term. You keep them maybe for 1 hour, 2 hours, 1 day. So maybe you know that on Black Friday, you need more workload and you need those dedicated workloads to be executing. So then maybe you just pay for 1 day for those slots. By paying for 1 day, you have your information coming in and it actually starts to get outputted. So this is one of the recommendations I would give using flex slot pricing for short-term usage. This ensures that you get the information that you need, the data that you need, the processing that you need for a very short amount of time. Yes, you are paying longer per second. Sorry, you are paying more per second for long-term, for short-term usage. But again, you're not committing to that 1 year. One very common example of this is for some of the AI capabilities of BigQuery. For example, if you wanted to build a recommendation system in BigQuery, you would need to use flex slots because recommendation systems only work with a fixed pricing model. but you don't want to pay a 5-year commitment just for recommendation and that you'll build in less than a week. So this is where flex slots can actually be quite useful. So let's assume that you have used the old flat rate pricing plan. Well, there is actually a time frame for you to move to Edition. The sooner the better. The good news is, if you are on that old flat rate pricing plan, is that the migration is almost always just metadata based. So your data doesn't move and you don't need to worry about that. BigQuery does have a migration tool that you can map your current slot usage to a auto scaling range with your enterprise tier. So what you would do in this migration is that you would set a minimum and maximum number that you're willing to pay for, and then it would scale within that range, saving you a lot more money. So the benefit of additions is that rather than just agreeing to 5,000 slots for sure, you could say, okay, I want a minimum of 1,000 and up to 5,000. If you use all 5,000, you obviously pay more. And what BigQuery Editions will do is it'll tell you, okay, this is how much those 5,000s are going to cost you. And if you are actually using less, then you only pay for less. So you would set, what's my minimum? Let's say 1,000 slots. What's my maximum? Let's say 5,000 slots. And then it would pick between those two based on your usage. You'll always know what the minimum amount will be and what the maximum amount that you will pay will be. So if you are using the old flat rate pricing plan, you should be migrating over to Editions. It's relatively simple to do, but you don't have to worry about it too much because it is actually very quick to do as well. And there's still some time to do it. So no major rush on migrating over to the Edition pricing. And again, that's for flat rate pricing only. Now, of course, we don't only just want to think about the terms and contracts that we build. What we also want to think about is, how do we make sure that we don't go over our budgets? Well, one of the great ways is that you can actually set custom quotas on BigQuery usage, meaning you can limit how many queries you can execute a particular day based on size. So I could say, I want to limit my BigQuery querying to a maximum of 500 gigabytes per day. That ensures that you'll never hit $6.25 per day, which is 1 terabyte of data. So you can control quotas. You can control quotas at a project and user level. So for example, you can say this project can never query more than 1 terabyte, or this user can never query more than 200 megabytes. You can actually do this at the quota option inside BigQuery's Google Cloud's Identity Access Management System. Another very popular option is to use cloud billing alerts. What the cloud billing alerts do is that they don't actually stop usage, but what they do is that they alert you when there's been above average usage. This way you can actually catch the problem before it escalates. So say, for example, your average BigQuery spending is $200 a month, and suddenly you're mid-month and you've already jumped to 300, well, your billing alert will automatically notify you of that, and you can fix it almost immediately. This will then give you an option to create what we would call a kill switch, which basically means stop BigQuery usage by controlling API access or user access. So you can track cost in BigQuery because all your BigQuery usage will be automatically in your custom cloud billing option. And then from there, you can build your custom billing alerts, or you can set project quotas. The great news about both of these is that they can be changed quite frequently. So let's say you set a project quota of 1 terabyte a day and you need more, very easy to change. If you want to limit it even further, like go down to 500 gigabytes a day, very easy to change. So you don't have to worry too much about your data usage. You can easily control that using quotas or use billing alerts to catch any major flags that might happen before they escalate to something bad. So now that we have a good understanding of optimizing our billing, and we also have a good understanding of optimizing our queries for performance, let's talk about one of the most incredible things about BigQuery, and that's its AI and machine learning capability. Now, if you've heard of BigQuery for a long time, you know that BigQuery is actually a SQL engine. But over the last 10 years, BigQuery is actually developed into quite a powerful artificial intelligence system. So let's see why BigQuery is such a good system for artificial intelligence. So first, let's talk about the AI simplified. What does BigQuery do? Well, BigQuery stores data, and BigQuery has a powerful analytical engine. Remember what I said, you can query billions of rows of data in seconds. What do AI systems need? They need a lot of data and they need a lot of computational power. So if you're using on demand, remember you have 2,000 slots or 2,000 compute nodes. That's quite a lot of power for your AI models. This is what gives BigQuery its amazing AI capabilities, because it stores the data for you and it gives you a powerful processing system, all at a very affordable cost. So how do we create machine learning models in BigQuery? Now, we're not going to go into deep detail in this course about how that works, but let's go over the major steps. First, we bring the data into BigQuery and we use BigQuery ML, which is BigQuery machine learning, to create the model to the data. You have popular algorithms such as linear regression, dense neural networks, decision trees, random forest, or even building your own, which we'll cover a little bit later. So now your data is in BigQuery, and you just now pass it to the BigQuery ML option, and then select what algorithm you want and what problem are you trying to solve. Normal ML algorithms that we get are for classification problems, regression problems, forecasting problems, recommendation systems, but now we also have the ability to create or modify large language models in BigQuery. So you can now have a very powerful Google Gemini model using the power of BigQuery to process your data. And in earlier slides, we talked about how Google BigQuery can also work as a RAG database for your system. So once you decide the model and the problem you're trying to solve, BigQuery can eliminate data movement, so any skeptical data or inefficient data or data that's not being useful, reduce latency, because remember, we have that Jupyter network that communicates very fast between Dremel and storage, and Dremel will be building the model. It can integrate with Vertex AI, which is Google's machine learning development platform, where you can build custom models, not using Google technology if you don't want to. So Vertex AI gives us the capability to use other technologies like PyTorch, GPT, and you can integrate them in BigQuery using Vertex AI. And then, of course, you can use the very popular LLMs or large language models. So large language models can actually be used in BigQuery, and it doesn't have to be just Google large language models. You can use Anthropic, you can use GPT, you can use any other model that Google's already built a relationship with. Basically, all the open source ones and the more popular ones in the market like Meta and Anthropic and such. And even in BigQuery, you can generate generative AI solutions. So you can build generated text, so like write a poem, write a screenplay, create an image. All that can be actually done in BigQuery if you choose to use BigQuery as your model generation. So you don't have to use BigQuery to create your models, but remember what BigQuery is giving us. It's giving us a very cost-effective large storage system and a very powerful cost-effective analytics system or computing power, which are the two key things that you need to build AI solutions. Now, what is another advantage of building models with BigQuery? Well, you have, of course, the SQL language. SQL is a very easy language to pick up. It's just a querying language. In the past, you had to build models using languages like Python and Java, which are very good languages, but they had a steeper learning curve. In my experience, I've seen a lot of people pick up SQL in just a matter of weeks compared to picking up Java and Python, which would take maybe a few months or years, depending on how good you are at learning. So SQL makes it really easy for us to write commands. And now BigQuery allows us to use that same SQL code for querying to build models. It has a syntax called create model, which will then allow you to deploy multiple algorithms. And it has specific problem solving syntax like ARIMA plus model for time series forecasting. So create model creates any algorithm that you want. This part of the BigQuery list. And technically, if you want to use TensorFlow, which we'll talk about later, or use pre-built algorithms and models that are ready to go like ARIMA plus. And you can also use BigQuery for transfer learning, meaning that you're taking a model that's been trained to solve a problem, like let's say forecasting sales, and then you can build your own model on top of it through transfer learning. So what you're doing is you're taking a pre-existing forecasting sales model, then you're building your own on top of it. So it's almost like two models working together. You have one model that's already been trained, and now you're adding your own data and your own information to it to improve it even further. So this can all be done with BigQuery, and it's very powerful when it comes to fast solutions and also efficient solutions. In fact, when I first started working with BigQuery, I didn't think it was very good at production quality work. This is like 2017, 2018 for ML, but I was very quickly proven wrong. I've actually built some very complex and quality systems using just BigQuery ML. So again, the SQL language makes it relatively easy for us to build these models using the BigQuery data storage and computational power. You can also evaluate models using BigQuery's evaluation technology. So in BigQuery, it's called ML.evaluate. And here you would get standard metrics like precision, recall, area under the curve. You would also get confusion matrix for your classification models. And then you can build a continuous development pipeline that can monitor the model, improve on it, and set up your own workflows that you can deploy from Git repositories or Vertex AI. So you can actually even do in BigQuery store different versions of the model with different features, maybe potentially different algorithms, and then do some sort of experimentation to test what is the best performing model and then deploy that one. And every BigQuery model can be deployed via an API to any endpoint that you want. Usually Vertex AI is the most popular option, but you can build a model using you can build a BigQuery model and deploy it to any endpoint you want after your evaluation process. The evaluation process in BigQuery also can create very useful graphs if it's easier for you to visualize or save for presentation. It's not just going to give you text-based answers. Now, remember, BigQuery doesn't just have to build models that are already there, like linear regression, dense neural networks. You can actually build your own custom models and algorithms. So BigQuery allows you to use TensorFlow, which is Google's machine learning numerical library, to build your own TensorFlow model. Then you can build your neural network on TensorFlow however you want and deploy that in BigQuery. Because what you do is that once you built it using TensorFlow's library, which is extremely flexible, and in fact, TensorFlow is one of the most popular machine learning libraries in the market today, you can then take that TensorFlow model and give it to BigQuery. So where's the advantage of this? Well, the advantage is that TensorFlow is extremely flexible in whatever algorithm you want. But now you're using that storage power and computational power that BigQuery has to improve on the model's performance. Because remember, the more data you have, generally your model will perform better. The more computational power you have, generally your model can perform better. And now you can create those custom algorithms that maybe you couldn't do with ML.create and BigQuery, but you can with TensorFlow. And then using Google Cloud Storage, you pass that model for TensorFlow. So what you're doing is that you're combining the data engineering capabilities of BigQuery with the data science capabilities of a solution like TensorFlow. TensorFlow, just to show you how powerful it is actually the base of the image recognition, video recognition technology that you see in Google. And in fact, just to show it, to give you something very powerful about TensorFlow, it's actually used by the World Wildlife Organization to check for deforestation or endangered areas around the world due to pollution and such. So it can actually operate to understand very complex problems. Now, remember when I told you that BigQuery also can work as a vector database, a RAG database for your solution. So just to have a very quick reminder, a vector database allows us to pass documents or additional information to our large language models. So our models can then use that data to answer a question, such as your 10-year sales report. So when you ask the model, hey, how have we been performing over the last 10 years? And any outliers, well, it can actually review all that data inside BigQuery. So vector search is one of the most complex things to do because what you're trying to do is that you're trying to find similar data points based on the prompt that you're writing. So for example, if I write, show me what's my best performing month, it's got to look through all my database. Or if I want to write, generate a sales plan that helps me grow at 10% a month. Well, it might look at all historical sales plan, but it's hard to get those matches. One of the reasons it's so hard is because it's so hard to store a large amount of data. But we already know BigQuery can store a large amount of data relatively easily. Another problem is when you have to search through a lot of data, it's computationally expensive. But we already know that BigQuery can query 1 billion rows of data in just a few seconds. So we have the capability of large data storage and very fast processing to perform our vector search. So when we perform a vector search based on whatever prompt or query we give, it can search those vector stores extremely quickly. And remember that each piece of text, whether it could be a word, a letter, or a phrase, or even a paragraph or page, will have a numerical representation. And BigQuery will use either Euclidean or cosine to potentially find the distance between the prompt that you're writing and the data that it needs to answer your question. So vector search is actually pretty common for using the most, finding the most relevant product images. So, you know, when you write inside a prompt like Gemini, oh, find me an image of a Nike shoe. Well, actually, it's using BigQuery vector search in the background to get you that image because it can search very quickly to get that answer. Now, remember a little earlier, I was talking about vector search functions in BigQuery. So let's say you have 100 million vectors. And if you had to compare your query to every single one of those 100 million vectors, it'll take a very long time. So earlier I was talking about vector inverted file index or vector search. It's like a library where you're matching your data. So let's say you have a sci-fi section. And what it does, it will cluster all your sci-fi content. So if I say, hey, recommend me a movie that's science fiction, it will automatically just search the sci-fi content because your vector search would have already embedded this into the model using BigQuery. So it doesn't have to look at all the content, all the type of movies and such. What if you wanted to write something like, give me a title for the new Star Wars movie? Well, it can actually just go to the sci-fi section, potentially even Star Wars section, and then it'll say, okay, these are the latest Star Wars titles. These are the oldest Star Wars titles. I think actually I'm going to call it this. So what you're doing now is that you're going through faster search processes using vector search or inverted file index, as it can be called. You would gain speed. You potentially could lose precision, but then you could just tweak it saying, okay, I don't mind for you to move slower, but to give me better accurate results. So that's what we would call using vector search, which we discussed a little bit earlier. Then, of course, you can use BigQuery as your RAG database. So a RAG database doesn't just have to be text-based or numerical based. It can actually be videos, images, and such. Now, BigQuery truly is optimized for text and numerical data, but it can also work with unstructured data for a RAG database only. So what is one of the advantages of using BigQuery besides speed and storage? Well, in BigQuery, you can actually control who can see what bit of data. So say, for example, you have the profile of all your employees, and you have an AI to help answer questions about employees or maybe human resource processes and such. So what does the RAG database give us? Well, it gives us the ability to search through that. But in BigQuery, you can say only these users can see all employees' data, such as salary. So you block the employees column. So when someone, let's say me, who's not authorized to look at employee salary, tries to say who's the highest paid individual, because I've already blocked that data in BigQuery, it will not return for me the results of that search. Very likely it will return some positive, polite response saying, sorry, you're not available to look at that data. Please review your access or request access to it. Now, one of the great things about BigQuery as a RAG database is that, again, it doesn't have to work with just Google technology. You can use the RAG database capabilities of BigQuery and deploy it on another LLM or use it outside of Google technology. So BigQuery can be your RAG database for any system you want to build, not just Google dependent systems. And again, because BigQuery has that processing engine and large data storage, it can very easily search through content very quickly and accurately to give the best answers. Not surprisingly, though, Gemini would have the best integration with BigQuery because there would be already native pipelines between Google Gemini and Google Cloud BigQuery. However, again, I repeat, it does not have to be just Google technology. Now, you don't need to use Python or a complex language to create a RAG. You can actually do it in a simple SQL statement. What you would do to create a RAG in BigQuery, a simple one a bit, is that you will use the select command to grab the 5 most relevant columns and rows. Again, just saying 5 is an arbitrary number for your vector search. Then you can concat all those rows into a single string of text and then pass that directly to a function like mlgenerate. So for example, if you're saying, I want a new Star Wars title, you can select the 5 most recent Star Wars movies, maybe customer feedback or audience feedback about how they felt about it, and then say, create for me a title for a new Star Wars movie using the ml.generate text option. So the rows of data that you use are going to serve as a context for your output. Now, again, I'm just using 5 rows as an example, but technically you can use the whole database, so you can actually look at every single movie inside your database very quickly. However, from a performance point of view, you probably don't want to look at the whole database. You want to look at what is relevant to you. Now, this is me actually controlling what data I'm going to see. However, you don't have to just control it yourself. You can actually have Google identify what is the most relevant rows and such. But in my personal opinion, I think it's always better to control this data yourself and suggest what should go inside the data and such. So it is that simple to create a simple RAG query. All you would have to do is actually pass the rows and columns that you want and see the results of that data. Now, let's talk about deploying models, because BigQuery is actually very powerful to build models, to improve models, evaluate models, or set up a RAG databases. But sometimes we need to deploy these models to mobile applications, embedded devices, websites, and such. All models created in BigQuery can be passed to Vertex AI. As I said earlier, Vertex AI is Google's machine learning development platform. This machine learning development platform can allow you to deploy models in a scalable and reliable way anywhere. So again, if you deploy Vertex AI, it can be used by any system, not just Google systems on its own. So BigQuery automatically connects to Vertex AI, and any model you build, you can choose to publish it in Vertex AI. And then for Vertex AI, you get all the security features, the additional ML features that you might not get in BigQuery. BigQuery, as I mentioned, can also access the Gemini models. And you can also use BigQuery to process large language model calls, so like generate text function across all the slots of BigQuery. So if you ever try to execute Gemini on your local machine, it might run a bit slow because you only have the power of your local machine. But if you execute it on BigQuery, it'll be extremely fast because again, you're getting at least 2,000 slots from your on-demand pricing. It also means that you don't have to export the data out for your large language models, because if your large language model, let's assume you're not using a Google model on Vertex AI, let's say you're using an Anthropic model on Vertex AI, there's already a native connection between your Vertex AI Anthropic model and BigQuery. So BigQuery can actually easily communicate with that Anthropic model, and it will serve as its database using Vertex AI. So Vertex AI, again, is Google's ultimate machine learning development platform, and it can be very easily connected to BigQuery. The reason that you want to use BigQuery and Vertex AI is because BigQuery has a lot of computational power and storage at a very cost-effective rate, and then you use Vertex AI to deploy anywhere you want or to other existing models, including non-Google ones. In BigQuery, you can also do multimodal analysis. So this is where we can do image detection. So like find a character or an individual in an image or a brand logo. You can use it for OCR. You can use it to scan video labels. So maybe scan a video, pass it to BigQuery using the ML capabilities of BigQuery and say, is this video child content or adult content? And then maybe block it. It can also use it to run analysis on the video. So you could pass it a video or an image and say, tell me more about this particular video and tell me what is the content about. Is this content safe for children? Is this content copyrighted? Things of that nature. So you can use BigQuery for these purposes. It does have the capability of multimodal analysis, not just for structured and text-based analysis. You can also take unstructured data like PDFs or just pieces of text and create vectors in BigQuery. So say, for example, rather than me passing a document, I just want to pass a long string. You can do that in BigQuery, and it can actually understand multiple languages. I believe, to the best of my knowledge, it can understand up to 20 languages, but that can be changed. So if I took a piece of text, let's say a poem or maybe a comment from a social media post, I can use the ML generating embedding model to embed that into a vector that I can then use for later. So for example, if I ask BigQuery, suggest me a caption for my Instagram post that'll generate a lot of likes. Well, in that case, I can use the generate embedding model to pass the caption. I already would have the likes data in some sort of structured format. And then I could say from here, give me suggestions on what would make a good caption. Now, one of the great things about BigQuery ML is that maybe you're not a great SQL engineer, but that's okay because BigQuery ML also writes SQL commands for you. You can actually use SQL for prompt engineering. So you can actually ask BigQuery to write this SQL command for you. And you can control typical things like the temperature or top K for creativity, ground the model to make sure it only uses the best possible SQL answers. And by grounding, I mean you're giving it a reference to know if it's writing the query correctly or generating the output correctly. And you can track token usage in BigQuery. Now, in BigQuery, you can also modify or fine-tune large language models. What do I mean by fine-tune? In fine-tuning, what I essentially mean is that you're going to train the model to understand your problem very carefully. So let me give you an example. Let's say I take a general large language model, right? And in this large language model, I want it to be able to recognize sarcasm. Now, by default, maybe the model is okay at recognizing sarcasm, but it's not great. So what if I passed it 10 rows of examples of sarcasm, saying, okay, when you see this, it's sarcasm. When you see this, it's not sarcasm. When you see this, it's sarcasm. Now, it's great to pass 10 rows. That's very useful. But what if I could pass 10 million rows? Wouldn't that take a long time? Not with BigQuery, because we already know about the computational capabilities. So now we can fine-tune a large language model using the computational capabilities of BigQuery to be ideal for our answer. Let's take a look at a more complex problem. What if I wanted a model, a general large language model, to actually write for me a user manual? Well, let's say the user manual is about how to build your own GPU. What I can do is I can pass it large amounts, manuals, and say, this is how you build a CPU, GPU, option 1, option 2, option 3, and each of those options include a different manual on how to build it. So then when I ask my LLM, give me a recommendation or tell me how to build a GPU, it already has the best possible output. Now, you can fine-tune outside of BigQuery, but again, to fine-tune those manuals, which is a lot of text, could take a very long time. But again, BigQuery gives us that amazing computational power. and it helps us fine-tune the models more efficiently and more cost effectively as well. And finally, with the AI, you can use large language models in BigQuery to clean your data, create anomaly detection, maybe use natural language to write SQL. So instead of you writing select from, you can say, pull me all columns from here, and it'll start to understand that. So you can actually build your own SQL agent for BigQuery using just the BigQuery ML capabilities. So what I want you to understand about BigQuery, besides the storage and computational power, is that it's now full machine, well, I wouldn't say full, but near full machine learning development tool that allows you to take advantage of those powerful capabilities to build AI solutions. And it's also gotten to the point where it's so good at understanding natural language capabilities that it can write SQL commands for you. So even if you or someone on your team is not a strong SQL practitioner, you can use BigQuery to write SQL. So in BigQuery, remember a couple key things that we always want to make sure that we're optimizing our storage, because again, the better our storage is optimized, the better it is for a RAG database. We're managing our querying costs, especially when we're using ML, because essentially ML queries do cost a little bit more than a standard query, and we can easily scale our applications using BigQuery and Vertex AI. So to summarize, BigQuery is a very powerful, fast, and scalable analytics solution. It really can help you turn your data into actionable insights. And I can actually tell you from experience, I've worked with a lot of organizations that might be on other clouds, but they still insist on using BigQuery as their main cloud solution because it is actually that powerful. Sorry, their main SQL solution because it is that powerful. It does support AI and advanced analytics. It is built to understand how to optimize cost and performance. It has strong governance policy that you can control how often someone uses it and when. And it also really is a tool to enable truly data decision making because it can give us fast insights at cost, process large amounts of data, usually structured and semi-structured, usually structured and semi-structured. Could also do some unstructured data, but there are potentially better solutions for that. And it can be integrated into large language models, Vertex AI solutions, and actually BigQuery is actually such a popular tool that it actually works with a lot of external solutions like Tableau dashboards, Power BI, and such. So overall, this was BigQuery masterclass on how to optimize BigQuery, how to use BigQuery, how to use the AI capabilities, and knowing what to do with BigQuery. Thank you very much.
Thank you, Francisco. That was very informative. Now, I know everyone's looking forward to the Q&A session, so go ahead and start putting your questions into the questions panel. And while you do that, I'd like to give the presentation rights over to Ifla, our product marketing person, who's going to introduce you to some of our fantastic promotions and webinar-related courses.
Thank you, Tracy. Insightful session. I believe everyone must have learned something new today or would have been able to brush up their skills around Google Cloud technology.
So firstly, I'm excited to announce that Netcom Learning is now an authorized training partner for Google Cloud, making us your go-to destination for cloud skilling. With this milestone, we are proud to offer comprehensive training across the three leading cloud technologies globally: Microsoft Azure, AWS Cloud, and now Google Cloud. So we, Netcom Learning, is your one-stop shop for cloud skilling. I would also quickly like to take you through some of our hand picked resources, which we think will immensely help in accelerating your Google Cloud skilling journey. Well, this document here that I'm presenting has been shared with you all in the handout section of GoToWebinar panel. You can download this document and access all the resources and browse all the offerings we have curated for you. So first up is the list of our recommended courses, which we feel will best suit your learning journey after attending our masterclass. So all these courses here are hyperlinked. Feel free to go through them post-event and check out the course descriptions and prerequisites and the value it can add to you and your team skill sets. Additionally, we have curated a blend of resources, including our upcoming and on demand events, as well as some informative and educational blogs. So you can make the most of these resources to gain extensive knowledge on the Google Cloud topics they cover. Also, here I would like to inform you that today's masterclass session is being recorded. So, in case you want to refer back to any of the topics that were covered by the trainer today, we'll be sharing the recording link with you through emails, and also you can access the link here on the handout so that you can revisit the session and learn at your own pace. Now, apart from our virtual sessions, you can also catch all the relevant updates related to IT and business training on our social media handles. So please feel free to follow us on LinkedIn, Twitter, and Instagram, and also subscribe to our YouTube channel for all the latest updates. Our official pages and channels are linked here on the icons. Finally, if you have any suggestions regarding the topics you would like us to cover in our upcoming webinars and masterclasses, please don't hesitate to send us a direct message or leave a comment on our social media posts, or you can just simply email us at google@netcomlearning.com. We would definitely try to come up with the sessions on your suggested topics. Thank you once again for joining us today. You guys have a good one. Thank you.
Thanks so much for guiding us through that information, Ifla. And now we're going to go ahead and jump right into our question and answer session. First question is, explain the difference between partitioning and clustering in BigQuery, and when would you choose one over the other, or perhaps use both?
That's a great question. So partitioning is normally when we want to divide the table on segments using a date or timestamp or integer column. So again, if you want to divide the table based on a date timestamp, so your table is now broken up into January, February, March, April, May, June, all the way to December in order, where your January data sits next to your February data. This makes it easier to search, because if I say, show me the sales for January and February, the data is next to each other, so it's easy to do. Clustering is when we're going to join the data using frequently used columns. So what do I mean by this? Well, let's say I'm looking at the sales for a particular city, right? So I'm always looking at the city of, let's say, New York. What it's going to do is it's going to make sure that the data is not randomized. It's going to say, okay, all the New York rows are going to be clustered together. So when you query New York, I don't have to search in that area of the storage system for New York, which might be next to Detroit, or it might be a New York row might be next to Boston. It will actually all be clustered together in New York. So clustering is when we're essentially saying we're going to put columns together based on the frequency of their usage. So again, if city is the most common column that you're using, it's going to group them by the city names together. So New York data will always be together, Detroit data will always be together, and such. Partitioning is always timestamp based or integer based. You can't partition on a string column. Clustering is usually based on high cardinality columns like user IDs, cities. And again, my recommendation is always using the columns that you tend to filter by the most as your partition columns.
Next question is, how does switching from logical to physical storage billing potentially reduce a company's BigQuery costs?
Yes. So logical billing charges based on uncompressed size of the data. Physical billing charges based on the compressed size of the data stored in the disk. So remember when I told you that BigQuery has a capacitor storage format? Well, what it does is that it compresses the data, so like repetitive data like logs or time series, and it keeps a footprint of that data inside its storage system. So physical billing is essentially a little bit more expensive because, a little bit cheaper because what it's saying is that I'm going to store this in the BigQuery slot drive storage versus Colossus because it knows I need to keep this data nearby and I'm going to store it and compress it in an efficient way that it's easy to read from the physical storage disk. So it can be cheaper because you're not really using Colossus long term. Logical billions where the data is uncompressed and it's usually stored in Colossus. Next question.
Next question. A query shows high wait time in the query plan, but the actual execution time is low. What does this indicate and how do you resolve it?
Good question. A high wait time usually means that there's not enough slots or available compute units, which are slots, to execute your query. So if you're using on demand, remember, you're not the only person using on demand in your project, and you're not the only person using on demand in your region for BigQuery. So if it's taking a long time for your query to execute, it essentially means that you don't have enough resources. Now, there's a few ways to do this. If you're using fixed rate pricing, you just get more slots, right? You just pay for more slots, whether flexed or long term. If you're using on demand, right, you can't buy more slots, your limit is 2,000. What you can do is that there is an option that is called non-interactive, which will essentially execute the query when there's enough slots available. Another option would be to communicate across your team on slot usage. However, when it comes to on-demand, your options are basically make sure no one's using it too often, or you use the non-interactive query option, which what it'll do is that you might still have a wait time, but it won't be a high wait time. It'll say, okay, I'm going to reserve the slots you need to execute this query from anybody else using them currently and execute. If you're using fixed rate pricing, much easier. You either just increase your slot usage by paying for more, whether it's flex slots temporarily or whether it's long-term deals, depending on what you need.
Next question is, what is the primary advantage of using a remote model in BigQuery ML instead of a standard built-in model like linear regression?
Yes. So a remote model allows us to perform tasks like sentiment analysis, text summarization, image recognition by calling a large language model or a TensorFlow model. So this means that the model is not built essentially inside BigQuery, which gives us a lot of flexibility because we can build that model however we want. A standard model in BigQuery uses BigQuery slots and structured data, and of course, we can only use the pre-authorized BigQuery algorithms like linear regression, random forest, and such. For example, BigQuery algorithms don't include support vector machines up to today. That might change soon, but a remote model will allow us to use support vector machines. So a remote model gives us the ability to perform more complex tasks because we have more flexibility in what kind of model we want. A standard model in BigQuery does not give us the same level of flexibility, though we do have a lot of different algorithms to choose from. And then, of course, a remote model doesn't have to be built using BigQuery hardware, like BigQuery slots, which could be expensive. It can be built on your own local machine, which is quote unquote free. Very likely you will build it on a more powerful unit, but you can do it on your own local machine.
And the last question of the day is, describe the workflow of a retrieval augmented generation pattern implemented entirely with BigQuery.
Good question. So the RAG pattern, essentially what BigQuery is going to do is it's going to take your text, usually unstructured text, and it's going to generate an embedding. So for example, let's say I pass it the entire work of Hamlet, right? Well, each of those words, letters, potentially even paragraphs itself will be embedded into a numerical representation. So let's say the phrase to be or not to be is going to embed it into the numerical number 88, right? So if I were then to ask BigQuery, finish this sentence for me, to be or not to be, it wouldn't look at the words to be or not to be. It would say, okay, to be or not to be is represented by the numerical number 88. What follows 88? Let's assume it's 99, and that is the question. So the full phrase would then be finish the sentence, to be or not to be. That is the question. So I'll use the ML dot in generating embedding to create that embedding. Now, how does it find the parent? Or sorry, not the parent, but the neighbor, like how to finish, that is the question, right? Well, it'll use vector search. Vector search, as remember, we talked, is going to create patterns and relationships between the different embeddings. So it might have looked at the works of Shakespeare and says, well, every time I see the numerical representation 88, which is to be or not to be, it's always next to the numerical representation 99, which is, that is the question. So it's going to then identify this pattern. Then when you use the ml.generate, which is where you would write your prompt saying to be or not to be, finish the sentence, or what comes after to be or not to be, that's when it will use the embedding and the vector search. It'll use the vector search to find the embedding first and then say, okay, what's my nearest neighbor? What usually follows 88? Okay, based on the data that you gave me in the RAG database, 88, which is to be or not to be, always follows 99, which is, that is the question. And that's how you get BigQuery RAG database working.
Once again, I want to remind you that as you leave this session today, you will be presented with a short survey. We would like to request for you to help us by taking a quick moment to participate in that survey. Your feedback really helps us understand your learning experience as we are constantly looking at how we can improve our future sessions. The survey answers are measured on a scale of 1 to 5, 5 representing outstanding and 1 representing poor. We want to thank all of you for joining us today, and if you do come up with any additional questions, feel free to send them to webinar@netcomlearning.com at any time. We hope that you found today's webinar informative, and we look forward to seeing you back here with us soon. Feel free to tell your friends and colleagues about our webinars and other courses. Have a great day, everyone.